Hello students, in this video we will be focusing on the third part of our unit 3 where we will discuss about what is known as synchronous sequential circuit design. So in this particular part the main focus would be on the design of this synchronous sequential circuit, and I'm just going to split this particular video into 3 different parts. So in the first part I'll be discussing about the different terminologies that are used while designing a synchronous sequential system, and also we will try to discuss about what is known as the timing parameters that are associated with the sequential elements as well as the combination logic circuits. Okay, so that would be the first part, and in the second part of the video I will try to address 2 important constraints. So these 2 constraints basically dictates the design process in a way that would lead you to design a synchronous sequential systems to function without any failure. Okay, and we will be applying these constraints under an ideal situation, okay, or condition, and that would be done in the second part of the video. And in the third part we try to find the feasibility of optimizing the design. Okay, so we will try to find the way by which we can optimize this design of synchronous sequential circuits, and later we will also spice up the design process by accounting the non-ideal behavior of the clock, which is nothing but the clock skew. So when we add this clock skew, then there are certain parameters that gets modified, and we will try to address those under this clock skew. Okay, yeah. So without further ado, let us focus on the first part, which is basically the terminologies and the timing parameters. And let me just write this again. And this video basically focuses only on this first part. Yeah. So the first terminology that we will try to understand is what is known as sequencing. Now, sequencing is generally means that we are trying to maintain a constant rate of float flow of data across different combinational logic circuits, or in general combinational blocks. Okay, so now let me just try to picturize this, what I have written down, with some sort of block. Let us assume that there are 2 blocks, okay, and it has multiple inputs as well as multiple outputs here. And in general, let us assume that the first block that I have drawn here is a combo logic of maybe an adder, and the next block is composed of one more logic where we have some sort of multiplier, and maybe the block that comes here may also get some sort of input from the other side as well. Okay, so you can also have 2 combo logics in parallel working on different datas, and then the output of these 2 combo logics are fed as an input to these things, okay, to the next combo logic, which is the multiplier. Okay, it's just an example. Okay, yeah. So now what would happen here is that in order to talk about the difficulty in doing such kind of design process, I just want to talk about one more terminology, which is known as the timing parameter, timing arc. So now timing arc is basically, say for example, I am just taken a combination logic. Okay, so basically the timing arcs can be defined for both combination logic circuits as well as for the sequential logic circuits, but here just for the explanation I will just take a simple example of a 3 input AND gate wherein I have the inputs labeled as A, B, C and the output is labeled as Y. and you could see that whenever the input A changes, there may be a change at the output. Okay, so this is one of the timing arc. Okay, so from the from the input to the output, we have one timing arc, and similarly from B to C as well as from B to Y as well as from C to Y. Okay, so basically these are the different timing arcs, or the path by which the output can change based on the change that is happening across one of the input terminals. Okay, so in general we call these things as something known as a timing arc. Okay, yeah. So with that, let us get back to our sequencing parameter. Okay, or the terminology. We know that whenever any data change that is happening across one of the input, it takes some amount of time to make a change at the output. Okay, now so let us assume that I have this same set of input signals like A, B, C, and any change that is happening at A would lead to some delay to get reflected at a particular output. Okay, now similarly the B would take a further delay. Okay, need not to be the same delay as that of A that has created a change at the output, but the B would take a much larger or lesser delay than compared to the A delay. Okay, or the timing arc that has taken from A to a particular output. Okay, since because we have multiple outputs here, there are different timing arcs that are possible in this case. Okay, so each one has its own timing arcs with respect to the output signals. Yeah, so now each of these arcs will have different timing values. Now you might wonder, like, okay, why do I generally bother about these different timings? Okay, now what happens is that basically when you change some set of inputs, okay, say for example 1 to 0, and you change the input of B also to 1 to 0 or 0 to 1. Now what happens is that because of these different timing arcs and different delays between these parts, the outputs in general will actually switch from the previous value, okay, and then to a new value, but before it just goes and settle down to a final steady state value, it actually makes some sort of glitches. Okay, just because of different paths that takes to remodify the output. Okay, so finally it goes and settle down to a different value at the output. Okay, now we always want an input to be fed to the next set of combo logic to be as a kind of refined inputs. Okay, we don't want to send in this glitches that are happening because of this different path delays that makes the output to actually make some sort of glitching over a certain period. Okay, so we call this as a kind of transient period where the data is not stable at all, and after a very long time what happens is that the data gets settled down to a well-known value, okay, well-known steady state value. Okay, so we want to avoid these kind of glitches that has been propagated through the multiplier and then to further stages. Okay, so we generally want to avoid these things. Now the way that one can avoid these things is by introducing some sort of sequential elements. Okay, so when I say about sequential elements, I am talking about either it could be a latch or it could be a flip-flop. And we know that the latch is basically a level sensitive circuit, whereas the flip-flop is basically a edge sensitive circuit, and sometimes the textbook would refer to both these circuits as registers. Okay, I guess I would have spelled this register only for specific to flip-flop, but I was wrong. Okay, so I will just try to use this opportunity to correct this mistake that I have done during the class. Okay, so in general the register refer to both the latch as well as the flip-flop. Okay, yeah. So now just by introducing some sort of registers between these combo logic, one could actually filter out these glitches. Now you might wonder, like, how exactly this could happen. Now we know that these sequential elements or registers, or more specifically let us assume a flip-flop, okay, a positive edge trigger flip-flop. We know that these flip-flops would read in the data only during the rising edge of the clock in case if this particular sequential block sequential element is a flip-flop and it's a positive edge triggered. Okay, now what happens is that we have to ensure that these edges are arriving only after the transient time of this particular output that is making the changes. Okay, so we want to avoid these inputs not to pass on to the next level. So we are trying to filter out these things by introducing some sort of sequential element between the different combo logics. Okay, and we are not introducing these sequential elements between different gates. Okay, so this alone can be a kind of 16-bit adder, or a kind of a huge, it can be even an ALU. Okay, so what we are trying to do is that we are trying to stabilize the flow of data at a particular constant rate, okay, by introducing these kind of sequential element when you process the data through a very lengthy lane of processing. Okay, yeah. So we have to ensure that these positive edges are coming in such a way that you try to avoid these glitches that were trying to propagate from the output of the first stage to the second stage. Okay, yeah. Now this actually does it, because we know that it only reads in the data only when this clock edge arrives. Okay, and by the time if your clock edge is happening after this particular output that gets settled down to a final value, then you are free to read out this particular value. Okay, so we have to design the system in such a way that we are having the clock edges in such timings. Clear? Yeah. But in turn, introducing these kind of sequential elements between the different combo logics, what happens is that you try to introduce an extra delay. And why the delay happens to be extra? Just because we are not able to send in the data from the previous logic to the next logic immediately. We were trying to hold this for a while until the clock edge arrives, right? So because of this, an extra delay is being encountered when you introduce these kind of sequential element between the different combo logics. Clear? Now that we call it as the extra delay that is being incurred because of the introduction of the sequential element. We call the as a sequencing overhead, or sometimes it is also called as a clocking overhead. Okay, so this is the definition with respect to the extra delay to get the final output. Okay, the extra delay that has introduced just because of the introduction of these sequential elements. Okay, so apart from this, it also introduces some area overhead. Okay, because in order to have this particular structure, we have to obviously spend some silicon area in your chip to accommodate these logics between the processing of your data. Okay, yeah. So now I just want to give an example of these kind of logics that you would have already seen. One of the sequencing example could be the well-known FSM, or finite state machine. Okay, you know that in order to hold the state of the machine, we need a kind of sequential block or a kind of register. Okay, and also you would have learned about the pipeline. Okay, so these are the two examples of sequencing. Okay, so when you introduce the sequencing into your system, the data flows at a particular rate. Okay, at a constant rate. Okay, yeah. Now the next thing that I just want to discuss is what is known as sequencing methods. Okay, so basically the sequencing methods discusses about the arrangement of the combo logic as well as the sequential elements in a way such that the system avoids any failure. Okay, so we have to arrange because as I said before, the system in general composed of two components. One is a set of combo logics as well as a set of sequential element. Okay, and this sequencing method gives us some sort of mean by which one could actually put the combo logic and the sequential logics in a way that the entire system can function without any failure. Okay. Yeah. So there are basically three types of sequencing methods. The first one being the flip-flop based sequencing method, and the second one is a two-phase latch system, okay, and the third one is the pulsed latch system. Okay, so these are the three different ways by which one could arrange both the combo logic and the sequential logic. Okay, and as the name suggests here, in the first sequential method or the flip-flop based system, we will be using an edge sensitive circuit, which is the flip-flop circuit for the sequential logic realization, whereas for the next two systems we will be using the latch circuit, which is a level based circuit. Okay, yeah. So now let me quickly give a glimpse of how does we arrange these structures. Okay, maybe I'll just take the picture of this to translate. The systems here. Okay, so as shown here, the first block is nothing but it's a flip-flop based system, okay, where you could see that the combo logic is being placed between the two flop circuits. Okay, and if you carefully see that these flops are basically driven by the same signal or the same clock signal. Okay, it's a single clock signal that goes to both the flop number 1 as well as flop number 2. Okay, so whereas in the case of a two-phase latch system, you could see that the combo logic is divided into two components, and between these two combo logic we have an intermediate latch as well. Okay, apart from the input and output, we also have an intermediate latch, whereas when you look carefully, the intermediate latch is driven by a different clock signal than compared to the input and the output latches here. Okay, now I'll talk about these timings and stuffs later on, but I just want to give a quick overview of these systems. Okay, and the way that the pulsed latch system works is by having only an input and output latch as we had it in our flip-flop based system. Okay, and in between those flops we would have, or in between these latches we would have a combo logic, and the system is almost identical to what is known as the flip-flop based system. Okay, yeah. So now let me focus on the timing parameters. So right now you are much more familiar with the terminologies, and now let me focus on the timing parameters. Yeah, so let me begin with the basic timing parameters, namely the things like rise time, and in short I would represent or label this rise time as TR. So it is defined as the time for the transition to happen from 20% to the 80% of the final value. Okay, sometimes one could also refer this rate at which it is moving. Okay, and the time difference between these two is what is known as the TR. Okay, and this is with respect to time, and there is a change in the voltage level. Okay, so this is my voltage axis. So how long it takes for me to move from 20% of its final value, there is this particular thing which mostly would be equal to VDD, okay, to 80% of the final value, and that is what is being defined as TR. But sometimes this TR can also be defined in the other way, from 10% to 90% as well. Okay, so there are two types of definitions that normally people used to adopt. Okay, but what we do is that we will restrict our definition of our rise time between 20% to 80%. Okay, we will not switch to 10 and 90%. Okay, in case if it is given also, you can just do it. Okay, yeah. So now the next timing parameter that I want to address is basically the fall time. So again, the fall time is defined as the rate at which the voltage value is switching from VDD to the minimum voltage value. Okay, at what rate it steps down. Okay, the voltage value steps down. So again, we will just use the same definition, like from 80% to 20%. Okay, so how long it take for me to switch from 80% of the final value to the 20% of the final value, and that time difference would then give us the value of T F. Okay, hope that these two definitions are well known before. Okay, and now there is also one more basic timing parameter definition, which is known as the edge rate. So this is just the average rate of both TR and TF. Okay, so which is nothing but is the arithmetic mean of both these quantities. Okay, yeah. And now let us shift our gaze to the other timing parameters that are related to sequential elements. Okay, and then later we'll just switch back to the other timing parameters. Okay, so now I'll just talk about what is known as the setup time and hold time. Okay, now we know that these two timing parameters are related to not the compound logic, but they are related to what is known as the sequential elements. Okay, so when I'm saying sequential elements, both these timing parameters are related to both the latch circuit as well as to the flip-flop base or flip-flop circuits, okay, or edge triggered circuits. Now basically a setup time is defined as the minimum time before the clock edge the data has to be the data input, okay, the data input to the sequential element, okay, has to be made stable, okay. So and similarly a hold time can be defined the same thing, the minimum time, but here the definition slightly changes at this particular point, where we have to maintain a minimum amount of time after the clock edge, okay, where the data input to the sequential element has to be made stable, okay. So let me define them with respect to a positive edge triggered flip-flop first, and later followed by which we will try to define the same set of definitions with respect to a positive latch, okay. Yeah, so now when it comes to a positive edge trigger, the setup time is defined before this rising edge, okay, as TSU, where I should not change the data input. Let us assume that the type of flop circuit that I'm using is basically a D edge triggered flip-flop, okay. So let us have a clock here, okay, and there are two inputs here. So one of the input signal is basically the clock and the other input is a D, and I just want to ensure that I can have any changes that are happening at the data signal well before this. I'm allowed to change the data well before the setup time, but after this I should not change. I have to hold the value of the data input as a constant, okay. Now, and the hold time is defined after the clock edge. As I said, after the clock edge it has been defined, and it is this, within this hold time your data also has to be kept stable, okay, and then later you are allowed to change your data input, okay. Yeah, so this is how the setup time and hold time with respect to a positive edge triggered flip-flop is defined, okay. So now in case if you have the negative edge triggered, the only thing is that instead of referring to a rising edge, we will refer to the positive edge with the same setup time being driven towards the left side, okay, and hold time defined towards the right side. That's it, okay. So this would be my TSU and this would be my TH for a negative edge, okay. Okay, yeah. So since because we are concerned about the positive edge triggered, I have to ensure that the data is kept constant or kept stable within this particular time zone, okay. So now whenever I have this kind of shuffling of things, it means that I can change my data and whenever the things that looks something like this, where I have no changes, there is no cross marking in these regions, then we assume that the data is stable, and the data could be either 1 or it can be either a 0. Okay, but you cannot switch between two different logic values within this zone. Clear? Yeah. So now let us focus on what is known as positive latch. Okay. Now, as we have discussed when we discussed in our unit second part, okay, we spoke about this latch circuit and also its setup time and hold time, but I'm repeating the same thing just for you to follow in the coming videos. Okay. So in this case, we know that since the latch is basically sensitive to the level, throughout the entire period, the data is allowed to read, and throughout this entire zone, my output Q is transmitted to the input. Okay, so whatever I have across my D is actually reflected at the output, just because of the transparency in this particular latch. Okay, so maybe let me have some data input here, and then you have some changes. Okay, but the setup time and hold time are basically defined with respect to the negative edge for a latch circuit, and again the hold time is defined after the edge. Okay, but it is defined with respect to a negative edge, and that's the basic difference between a positive latch and the positive edge triggered flip-flop. Okay, yeah. So within this zone, you are not allowed to change your data, so you have to ensure that the data is kept constant within this particular zone. If it is 1, then the same data will be held. Okay, and after that, so throughout this entire zone, I could able to read out my D data onto this output Q. Okay, onto the output Q. So I'll just draw the corresponding output here. So whatever be the thing, throughout this entire zone, when the clock is at 0, I'll be holding some previous data, and then later I'll try to read in this data input at this particular point, and then the data keeps changing, and due to which the output also keeps changing, but certainly there is a delay between this edge as well as the output Q edge. Okay, they are not happening instantly, but after some delay. Okay, and then you are changing the input just well before the setup time, and that input is read at the output, and after then the data at the Q is held constant. Okay, because after then you are turning off the latch, and due to which it holds the previous data. Okay, so now what is more concerned here is that we should never change the data in this particular zone where the setup time and hold time is defined. Okay, so in a way, what I can do is that I can equivalently represent this particular picture in terms of the way that I represented earlier. Okay, so you are being allowed to change the D input throughout the zone. Okay, and after this you have to ensure that the data is held constant. Okay, and after then you are allowed to change again. Clear? And again, because the latch would be in the hold mode, there will be a stable output, but once the latch is on, then the changes at the input is being reflected at the output. Okay, and then just because the input is held constant throughout this zone, you would be having an output which is whatever the last data that is read in will be reflected at the output here, and after that, since because we are in hold mode, your output Q will never change after this. Okay, till you get into the positive cycle again. Clear? Yeah. Yeah, so I hope that the timing parameters that are related to the setup time and hold time with respect to both latch as well as the flip-flop has been defined. Okay, and in general, this is the set of timing parameter that is more or related between the input and the clock. Okay, so now let us discuss about the timing parameters that are associated with the output and the input signals. Okay, so the input can even include the control signals, which I will discuss right now. Okay, yeah, so these are nothing but the propagation delay and the contamination delay. Now you might have already heard about these two delays when we discussed about the combo logic, and as you guessed, both the propagation delay and contamination delay is applicable for combo logic, which is a well-known fact from the previous unit. But one more thing is that it can be also applicable for sequential circuits as well, or sequential elements as well. Now, whenever we refer to a flip-flop circuit, both this propagation delay and the contamination delay are basically related between the clock and the output signal. Okay, whereas in the case of a combo logic, the propagation delay and the contamination delay are basically related between the input and the output signals. Okay, whereas in the case of a flop, it is related to the clock and the output signal, and we generally call this particular delay, either it is a contamination delay or a propagation delay, the relation between the clock and the output, we call it as a clock to Q. Okay, and this clock to Q delay can be either categorized as a clock to Q propagation delay, or it can be called as again clock to Q contamination delay. Okay, so I have not discussed much about the propagation, the differences between the propagation delay and the contamination delay, just because we have already seen when we discussed about the combo logic. But just for recall, I'll just try to define it again. So a propagation delay is something like where your output change at the input is directed at the output after a very long time. Okay, whereas the contamination delay is something known as a minimum delay, where the change at the input is reflected at the output immediately. Okay, so that's the basic difference, but we'll just see these basic differences with some set of timing diagrams. Okay, yeah. So first we spoke about this flip-flop, and now let me discuss about the propagation delay and the contamination delay with respect to the latch circuit. Now, as we know that the latch circuit is a level sensitive circuit, and because it's a level sensitive circuit, any change of data that is happening inside this can also affect your output. So there is a possibility that the D can affect your output, or if you are holding the data as a constant, okay, just well before the rising edge of this particular signal, then the output is would change only because of the clock. Okay, so there are two possibilities, and so one is you are trying to stabilize your data well before the clock edge, and the moment the clock edge is happening, the clock is the one that modifies your output. Okay, so in that case you have a delay between the clock to Q as we had it for the flip-flop, whereas on the other case, since the latch is transparent throughout this entire zone, which has been marked here with the blue one, okay, any change in these zones will actually affect your output as well. Okay, so because of this, we also have what is known as a D to Q delay. Okay, so let me just summarize that. So there are two types of delays that comes here. One is relating your clock and the output, okay, which is called as clock to Q delay. And again, this clock to Q delay have two versions. One is the propagation delay, which conveys our maximum delay, and you have contamination delay, which conveys the minimum delay. Clear? And there is also one more type of way by which the output gets modified is the relation between the data input and the Q. Okay, so we call this generally as a D to Q delay. Okay, yeah. So again, one could decompose this D to Q delay as something known as contamination delay and the propagation delay. Okay, depending on whether this particular output Q had changed the output with minimum delay or with a maximum delay. Based on that, we will have two type of delays. Okay, so probably my words might not reach you properly. So what I do is that I will just try to reflect the same phenomena with some set of timing diagrams. Okay, so let me just begin with the combo logic here. So as said, the combo logic has both the type of delays. One is the contamination delay, the other one is the propagation delay. Now in this case, it is shown something like A and Y. So basically we have some sort of multiple input as well as multiple outputs. And what happens is that, as I said before, there will be some sort of glitches that is happening before the output finally gets settled down to a single value. Okay. Just because of the multi-input and multi-output principles. Okay, so this combo logic can be even a 16-bit parallel ladder. Okay, and when we had a 16-bit parallel ladder, we know that when there is a propagation of carry, the S0 would be produced, like the S1, the sum at bit position 1 would be evaluated first, and then later S2 would be evaluated, and in that way, all the way our S16 output would be produced. Okay, so what is happening is that I'm not getting immediately the sum output of all the 16 bit at a single time. Okay, whenever there is a propagation of carry through this carry chain. Clear? So due to which the output starts the entire output like S1 to 16. Okay, so basically they start at some predefined value, and then later it takes some amount of time to make the individual bit to change. Okay, so in a way that this output previously might be at a particular state, okay, and then it keeps toggling just because the first toggle would have happened just because of this S1, the second toggle would have happened because of S2 getting updated for the new sum. Okay, so in that way you would have some sort of delay, and finally the output of all of these S1 to S16 would be available. Okay, now we call the delay where the S1 is output has been reflected, we call as a contamination delay, whereas the propagation delay is evaluated when all of the outputs are stabilized and finally got its output here. Okay, so we call this particular delay as the propagation delay. Okay, so in the previous case when we discussed about combo logic, about the contamination and the propagation delay, we had only single output. Okay, so in those kind of phenomena, there won't be much delay between this TPD and TCD. Okay, so there won't be much of changes that is happening at the output, or not much of glitches that will happen to the output here. Okay, but this kind of phenomena happens when you go for multiple outputs conditions. Clear? Yeah. So now let us focus on the timing parameters associated with the flip-flop circuit. Okay, so as shown here, you could see that the setup time and hold time for a positive edge triggered is defined between the clock signal and the input with the blue one that I have marked. Okay, and also you could see that the clock to Q delay have both the contamination as well as the propagation delay. Okay, so depending on the type of input that I have here, so either if it is a 0, then the clock to Q delay would be minimum. Okay, if you have a data input which is 1, then the clock to Q delay would be maximum. Okay, depending on how the transistors are being attached inside this particular circuit. Okay, yeah. So basically we have two type of delays, and we generally have the contamination delay as TC and contamination clock to Q. So the first C represents the contamination part and CQ denotes your clock to Q delay. Okay, and similarly the TPCQ denotes that we are talking about the propagation delay, which is the maximum delay right from the clock to the output to get modified, and it's about the delay between the clock and the output signal. Okay, yeah. So now let us focus on the final timing parameter of the latch circuit. Yeah, as shown here, you could see that the setup time and the hold time for a positive latch is defined with respect to a negative edge. Okay, yeah. So now let us focus on the other two parameters that are related to the outputs. Now here you could see that the data is held constant when the clock is making a transition, and due to which it is the clock that modifies the output over here. Okay, and due to which we have a definition of clock to Q for both contamination as well as the propagation. Okay, but because the latch is transparent within this zone, okay, let me just mark that zone where you are allowed to change your data input. Okay, so just before the setup time you are allowed to change your data input, and due to which you have the entire freedom to modify the data throughout this entire zone. Okay, and because of this you could see that there is a change that is happening at the D input, and that also can affect your output, and that delay we call it as D to Q delay. Okay, and again you have two different versions of the delay. One is the contamination, the other one is the propagation delay, just because it has taken a very long time for us to change the output. Clear? Yeah. So with this I'll just complete this part 1 of this particular video. In the next video we'll just talk about the sequencing methods, and we'll try to impose the two important constraints which are nothing but the maximum delay constraint and the minimum delay constraint. Yeah. Thank you. Until then.